Hello, everyone, and welcome to another episode of the MATLAB and Simulink Robotics Arena. In today's episode, we're going to talk about LQR control for an autonomous underwater vehicle. And joining me today, I've got a couple of team members from the Autonomous Robotic Vehicle Project out of the University of Alberta. Hello, Nathan and Juan. Welcome to the Robotics Arena.
Hi.
Yeah, thank you for having us.
Do you guys want to go ahead and just introduce yourselves and your team a little bit to our audience?
So the Autonomous Robotic Vehicle Project is an extracurricular student vehicle group that gets sponsored by the University of Alberta. And basically our club, every year there's a competition in San Diego called RoboSub. And so every year our team designs and builds a new robot, and then we take that robot to compete in San Diego. And basically the competition is this epic underwater obstacle course. And so the robot has to be able to accomplish a bunch of things, like going through a gate, identifying objects, manipulating objects.
Awesome. Well, thank you for taking the time out to talk to our audience about the work that you've done. So for today's agenda, Juan and Nathan are going to go over what a linear quadratic regulator is, and then we're going to talk a little bit about the difference between an LQR and a PID controller. PIDs are obviously things that you guys in the audience are familiar with. Then they're going to talk about the control scheme that they employed for their sub, and then we talk a little bit about modeling the vehicle dynamics, and then we do software demonstration and point you guys to key takeaways and resources. So without wasting too much time, I'm going to hand it over to Juan and Nathan. And
So the main focus of an LQR system is to take a target and try and hold it. So yeah, basically what we do is we take a system of equations and then linearize them, and then we get these matrices that describe the physics of our system. And using those, we can optimally hold a target state.
Basically, a control system is anything that's related to the movement of the robot. So if we want to move the robot from point A to point B, or achieve a certain configuration from A to B, then our control system is what gets us from a point A to point B. And then what an LQR controller is, it's an optimal control system. So we want to get from point A to point B in the most optimal way as possible. And then we use that, and then we do that by using a representative model of the robot physics that we basically put into the controller. And that's how it achieves the optimal control.
Okay.
Yeah. So the LQR controller generates the control laws using four matrices. These are the A, B, Q, and R matrices. The A and B matrices basically are what model the robot's dynamics, physics, and then anything related to the control dynamics as well. The Q and R matrices are more related to the cost. So that's where we kind of specify what's the most important target or part of the state to hit. So for example, for us, holding depth is really important, because if our robot ever surfaces, then we get disqualified. So the Q and R matrices basically just allow us to, I guess for lack of a better term, tune our controller. The reason why our team switched from PIDs to LQR is because we were finding that it was taking a long time to calibrate our PIDs. We would have 3-hour slots when where we would book a pool to test the robot, and out of that 3 hours, we were spending like an hour at least just tuning the PIDs. And any time that we made a minor modification to the robot physically, so like if we added some component or some new mechanical device, that would completely throw off our calibration. We'd have to start all over again.
Okay.
And so as we were getting closer and closer to competition that becomes really critical, because things happen very fast, and every day we're always making some modification to our robot. And so it just became really unfeasible to keep calibrating the PIDs. Mm-hmm. And so with an LQR controller, because the physics are already kind of implemented into the controller, it actually allows for a lot less intensive calibration. So there is some calibration that's required, but right now it takes us at most half an hour if we want to do a very thorough job.
Okay.
Another thing with the PIDs is that they kind of limited the movement that we could do. So before, we could only control 4 degrees of freedom out of the 6. But with an LQR controller, because it takes into account the entire robot state, so like the depth, XY positions, velocities, and orientation, it actually allows us to control all 6 degrees of freedom, which allows us to do much more complicated maneuvers if needed. And of course, when you have one controller versus 4 separate controllers, it definitely simplified our software architecture. So that definitely made it a lot simpler to not only to use, but then also just to, I guess, explain to other people.
Nice. Okay. Cool.
The way our system works is it's basically a collection of nodes that are independently talking to each other. And the control of the flow of data goes from our sensors to our motors. And to do this, we have multiple inputs. We have our sensor data, and we have our mission planner. So basically what an LQR controller takes as input is the current state and the target state. And so with our sensor data, we can get very high frequency input of our sensor state, and which gives us our current state after passing it through a state estimator. And then we take our mission planner, and then that goes into the LQR controller as well with the target state. And using those two things, we use the LQR controller to then pass raw, like physical, like percentage controls to the individual motors.
Okay.
So we will play a video of our robot performing a barrel roll in the simulator. So our simulator for our team is basically a Linux simulator. We base it off of an existing package, and then we use our simulator to kind of proof test proof of concept for our LQR controller.
So one question that I have while this video is playing is I know a lot of teams struggle with modeling the water around them, especially in for submarines when everything's underwater. How do you guys sort of deal with that? Is that something that just comes along with the package that you all use, or have you all modeled the physics yourselves?
So as we mentioned, the kind of what makes the LQR controller very, very cool is that we actually like program the physics into the controller.
Okay.
And so what ended up happening is that the package that we got for the simulator, it already had like a pre-existing physics model for underwater, and we ended up looking at that physics model. We kind of upgraded it quite a bit, and then we ended up actually basing the physics of the controller from that physics model.
Yeah, okay. And the key components of that those physics is we have a linear drag and a quadratic drag, and that basically models the water. I mean, it's not perfect, but it's computationally tractable.
It's a good starting point, so to say. Okay, awesome.
Yeah. So to answer your question, yeah. So there wasn't a pre-existing physics model, but we definitely upgraded it quite a bit, and then ended up using that upgraded physics in the actual controller model.
Okay, cool.
One of the most challenging parts about developing the LQR controller was actually getting that physics model to work properly. Nathan and I, we read a lot of textbooks. We looked at a lot of different resources. We kind of looked at something that some other teams and what they were doing. We ended up coming across a really good textbook that had a lot of the equations that we needed. But the big challenge was, okay, how do you get those equations into the actual controller? Because these were very, very big equations with massive matrices, with many, many terms. So what we found was that MATLAB actually had pretty good symbolic functionality. So what that allowed us to do was just kind of very easily transpose the textbook equations into code. Okay. And then the advantage of using the Symbolic Toolbox, which was probably one of the main advantages of using MATLAB, was that we could actually just linearize it using the Jacobian. Okay. And linearization is very, very important because LQR stands for linear quadratic regulator, so it actually only works for linear models. However, our physics model is actually nonlinear. So because by being able to linearize a symbolic function, we could actually just get a function that was based on any given state. And so what that allows us to do is we can actually linearize real time. So for every single state that the robot gets, we actually linearize those physics at every iteration. And that's pretty cool because in talking with a lot of teams, they would just kind of pick some of the teams would take kind of set points and then just linearize around those set points and then just kind of approximate. So having like a real-time linearization was really, really beneficial for us.
Okay.
So once we linearized the symbolic equations, we used MATLAB's ccode generator to actually to convert it to ccode, and then we manipulated the strings a bit to get it to get the variables and the matrices into proper Python form, because our current controller is in Python.
Okay.
And then we basically run a script. Anytime we want to update our model, we'll change whatever parameters we need to change. We run a script that will update the matrices. It outputs a text file, and then we will just copy paste that text file into our into another Python file, and then that's what's used in the controller.
Okay.
And then what you see on the slide here is actually one of the very first basic LQR tests that we did. So it's just a very basic depth test. So the top plot, you kind of see the robot's pose. So the XYZ positions and then the orientation. The bottom plot is the velocities. So yeah, it was just a very, very simple depth test. I remember that was very significant. It's the first time that everything kind of came together.
Okay.
So this was definitely like step one, and then simulator was probably the next phase, and then implementing the actual robot was the last part.
Okay.
Yeah, so that's kind of the brief overview of our control system. Kind of to what we were talking about previously. This first script that we just called symbolic state space is just where we generate our symbolic functions. So we start by declaring a bunch of symbols, and then it was very simple. It was just looking at the textbook and just literally just copying out the variables.
Yep.
And then our thruster configurations. Yep. So various equations.
So just a bunch of complex math. That's all that.
Yeah. Just
Okay.
Yeah, and then just a lot of complex math.
Okay.
Yeah. So that's the first one. The next one is where we so anytime we want to change our model, this is where we would specify the different parameters. So here we have the water density, center of gravity, center of buoyancy.
Okay.
Displaced water volume, our mass, which always changes. All our drag parameters. So this is where we would actually modify the model.
Okay.
This was really handy using the subs function to actually substitute the variables into the symbolic function.
Okay.
And then finally, we just linearize the function into. We first linearize it about the state, which gives us our A matrix.
Okay.
And then we linearize it about the control output, which gives us our B matrix, which were 2 out of the 4 matrices that we needed to run the controller.
Yep.
Right, and then and so our A matrix is actually a function of our state. So then at every iteration, we can actually put in the state, and it'll give us a linear approximation of our physics.
Okay.
And then our control, we actually just made it constant because it just made more sense to leave it that way.
Okay.
Here is just this is the script where we will run the previous 2 files, and then this will basically just output the results into a text file.
Okay. Which is what your Python controller needs to run. Okay.
And then we just use string replace to manipulate the strings to get it in the proper format.
Yep.
So it's just an easy copy paste.
Correct.
Which is really what we wanted.
How would you guys go about doing this copy paste? Could you run it for the benefit of our users and see what it looks like, what your text file looks like at the end?
Yeah, sure. So we will run it. So the model's been updated. So now it has created a text file. So what you see here is what the MATLAB script outputs. So we have our B matrix, we have a couple of other matrices that we need. This is our massive A matrix. So maybe here anyone can appreciate how nice it is to just have it all automatically output for us.
Yeah.
And then the copy paste is really simple. So we would just so for our B matrix, we would just copy, and then in our params file, just tells us exactly where where it goes. And then there we go. And then we would just do that for the other matrices.
For the others as well, and then you just upload this into onto your robot.
Yeah, and then we can just run the Python code or Python controller in the robot.
Okay, cool. That's seems pretty simple for something that's really complicated to do. So what were you guys able to achieve by doing all this? Was there some particular thing that you all were looking for when you started off with this project, or was it just to make your life a little easier when you switched to this method versus the PID method?
Yeah, so the PID controller it worked really well for basic movement, but one of the challenges during one of the years was to actually move in as many degrees of freedom as you could through a gate. So basically doing like barrel rolls and like complicated maneuvers.
I believe they call those style points at RoboSub, right? Okay.
Yeah, so with that requirement, like the PID controllers just weren't going to cut it. So yeah, that was the original inspiration, but as we went forward, like the ease of tuning, the flexibility, that's really what won us over in the end.
Okay, cool.
So currently, once we update our model, anytime we update our model, we can just run our controller as is. But during the development, we actually made like a MATLAB specific controller, and this is basically this is basically just a simpler version of what we run in our actual robot.
Okay.
It's just in MATLAB. Yeah. So we made this using the ROS Robotics Toolbox. Definitely worth it. Yeah. This is what we used to prototype. The controller before we moved it all into Python. Okay. Yeah. And then the reason we moved it to Python was just so that we could run it untethered with the robot.
Yeah. That's what works with your entire code, with your entire system.
Yeah. Yeah. Just because of our hardware constraints. Yeah.
Correct.
Okay. So basically, what this file does is it just it'll just connect to the ROS master, and then it'll just run a control loop. It just the control loop just basically calls the LQR function, and then it'll just input whatever state it gets from the sensors, and then in this case it'll get the state from our simulator. So we can boot up the simulator. We'll also boot up our state sensors, and then we can boot up just RQT, which makes life a little bit simpler. We can start the node. Okay, so this is our simulator. So now we can actually put in target state. So this is just a GUI that our team uses, just using Qt Creator.
Okay.
So we're just going to tell it to go to a certain depth at 2 meters. We'll see the node is now running. It takes a little bit of time, but once it gets started, you'll see it's actually diving. And then here it's printing what the thruster outputs are. So these are like percent effort. Now, just to be fully transparent, we've actually tuned this controller just so that it works perfectly in the simulator. So so in real life, these commands probably wouldn't work, but just for the demo part.
But this is actually running with MATLAB in the loop. Your control commands are being computed.
So here we dove. It's pretty stable. So now we can get it to do a bunch of other things. So if we want, we can just give it a velocity. And then that will get it to move forward.
Just move forward, yeah.
Here we can actually see our state.
Correct. Okay. So
you can see that our depth's pretty stable. Ideally, we'd want this to be as close to 2 as possible.
Yep.
But this is just like a tuning issue more than anything else.
Yep.
So let's just give this a 10 coordinate. So one of the very beneficial things about our LQR system was that we could actually use we can actually like localize. We could actually localize underwater.
Okay.
This was LQR, and the fact that our team was able to get a very cool sensor that allowed us to measure velocity underwater, and then putting the two together actually lets us use positional control,
Okay.
which very few teams could do, and we're still kind of like fine-tuning our positional control, but just the fact that we can do it is pretty amazing.
Yep.
Yeah, so this is
Cool.
basically the gist of our controller.
That's cool. It's cool. Well, thank you guys so much for showing us this code. I think a lot of teams can benefit from, more than anything else, just ideas as to how they could control their robots, going into the future. Thank you so much, guys.
It's all good to see it in the simulator, but this stuff actually does transfer to real life. And this is when we first tried to do a barrel roll.
Okay. Oh, nice. That's actually a pretty complex maneuver. I've never seen a team do this at RoboSub ever, so that's good.
Yeah. So the key here is like we're controlling like multiple things at once. Like we're controlling the depth and we're controlling the roll at the same time, which would be really hard with PID controllers.
Yep.
Yeah. So to do a barrel roll, you just give it a forward velocity, angular velocity, and then just hope that it can maintain the depth, I guess.
Yeah. Okay, awesome.
So I guess the key takeaways here is that, LQR is kind of like a plug and play thing, but the hard part is getting like the vehicle dynamics, and that's really what's going to determine your success here.
Okay.
And that MATLAB like really did help us a lot with that. The symbolic equations, MATLAB in the loop, was really helpful, like definitely increased our velocity. And as you can see, like when we send commands to the robot, LQR like really helps you because you can send like a unified kind of command, and you don't have to really worry about much. Like if you want it to go to a certain state, you just send that target state, and it basically works. So yeah.
Okay. So for the benefit of our users, what is the name of the textbook that you guys referred for these equations?
Okay, it's called Handbook of Marinecraft, Hydrodynamics, and Motion Control by Fossen.
Okay, cool. Well, thank you guys so much for taking the time out to present your work here. So before we wrap up, I wanted to point you guys to resources. You can get in touch with the Robotics Arena team either on Facebook or through our email address up there, and then also don't forget about the software offer. We do offer complimentary software to a number of student competition teams, and you can find out more at the link on the screen. Thank you so much, Nathan and Juan, and it was a pleasure having you in the Robotics Arena, and we hope to see you again sometime.
Yeah, thank you very much.